Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Yeah, okay. Just give me 1 minute. Okay, so we'll start with this question. I hope you have you got some time to go through the write-up that Professor Das prepared for NFAs with epsilon transition and how they do not have more power than a normal NFA or a DFA. So the question is, you consider this NFA with epsilon transition, with one epsilon transition for the language a to the I, b to the j, such that I and j are greater than equal to 0. So epsilon is also in the language. Now you have to convert to a DFA that accepts the same language. So in order to construct the DFA, what are the components that you need? So over here you have this you have the set Q, which contains two states P and Q, and you have this transition diagram. You have this set of transitions where you have one epsilon transition. So how will you define a multi-step transition function?
Ma'am, it will be the same except capital delta of p comma epsilon will be p comma q.
Capital delta of P comma epsilon How will you use this to construct the DFA? So epsilon is not part of sigma, so you're taking it over some sigma dash, which is sigma union epsilon, right?
Yes, ma'am.
How are you using this to define an equivalent DFA?
Ma'am, can we do something like this, that in the NFA diagram, we can make P as the start state, right? P as the final state as well, means P as the accepted state, replace epsilon with B, and from
Epsilon
Q,
with B.
yes, and from Q, if we get an A, we go to a state which is not a final state, and from there we stay there, and from that third state we stay there.
Okay, I'll just draw your whatever you're saying. You are taking just give me 1 minute. Can you see my screen?
Yes, ma'am.
Yeah, okay. So what were you saying? You make P a final state, and instead of you keep A,
And
and
instead of epsilon, we write B. Then we make Q also a final state and keep the direction of B same. And if we get an A from here, we go to another state R from where we cannot exit. Means now it will stay here only, whatever you get. I think this should work.
okay, let me see. Yes, I think this works. So what can there be? You have strings of the form a to the I. You have epsilon, L is equal to epsilon, union strings of the form a to the I such that I is greater than equal to 1, union b to the j such that j is greater than equal to 1, union a to the I, b to the j such that I and j is greater than equal to 1. Both are greater than equal to 1. So epsilon is accepted at P, a to the I is accepted at P, b to the j is accepted at Q, and a to the I, b to the j is accepted at Q. Anything else will go to the sink state R. Yeah, I think this is fine. I'll leave the exercise over here, but there is this particular example. You were able to figure out a DFA easily. Please go through the write-up. There is a process in which you can convert an NFA. There is a procedure in which you can convert an NFA with epsilon transitions to a DFA. Or there is actually also a procedure that gives you a conversion to an NFA itself, where you can get rid of the epsilon transitions. So go through it. Let me go to the, yeah, okay. Okay, so we were at this particular example where A is a regular language over 0, 1, and we proved that the language B, which is XY over 0, XY in 0, 1 star, such that X1Y is in A is regular. We proved this. Now the second part is you have to prove that the language C, which is X1Y in 0, 1 star, such that XY is in A is also regular. Okay, so if XY is in A, so consider you're including those strings in C such that there exists a Z in A such that Z can be broken into X comma Y, and this particular string in C, Z dash in C, is equal to X1Y. And you have to show that this is also a regular language.
Ma'am, in the NFA, we can make a loop for one at each node.
Okay, so for A, suppose you have an NFA. Suppose you have a DFA. Let's say you have a DFA for A. Because A is regular, so you have some final states and you have some transition. So this is some M such that L of M is equal to A. Now what are you saying?
Ma'am, I'm saying for NFA.
Oh, okay, so you can assume this is an NFA as well. Now what are you saying?
So, ma'am, at each node, we can make a loop for the character one alphabet.
We
So that,
can
ma'am,
make a...
if like from start node to this node, it is X, and from this node to the final node, it is Y. So we can add one also in between.
But I can go around this loop more than once, right? So,
Yes, ma'am.
so suppose you have X. Suppose you have a path XY. You did not have this 1. So suppose XY belongs to A and x111y does not belong to A. Then notice that x111y can now be accepted by this path.
Okay, yes, ma'am.
Ma'am, we can make the make 2 copies of this DFA,
Okay.
and then from one, like if we call a node P in one of the DFA and a state P dash in another, then we can just add one transitions to make it an NFA from P to P dash, and then keep the end states at P dash, the second copy.
Okay, let me try and see what you're saying.
Yes, ma'am, we can do this.
So from every P to P dash, I'm keeping a one transition.
Yes, ma'am.
Okay, so now prove why this will work.
Ma'am, for any
So you have to
for
prove
any-
2 directions. Tell me which ones you're proving.
ma'am, first of all, I'll prove that if xy is in A, then x1y will get accepted by this NFA.
I'll call this NFA N. Okay?
Ma'am, so the DFA uniquely defines the path. So let's say in the NFA, in the DFA M, the path that corresponds to X be S0, S1 up to SM.
Sorry, 1 minute. Unique path labeled XY. So let's call S to S1 up to SN. SN belongs to final state. Okay?
Ma'am, this path can be broken down into
So
S.
there is a P somewhere.
Yes, ma'am.
Hmm.
So S, let's say P equal to SM.
So I think this is what you're trying to say. Delta Sx is equal to P.
Yes, ma'am.
Yeah, and then delta hat Py is equal to Sn.
Yes, ma'am.
Okay?
Ma'am, so the final, so in the NFA N, the string x1y will have one of its corresponding paths as delta as S to P, followed by P to P dash, and then P dash to Sn.
Yeah, I'll say Sn dash. Yeah, okay. Okay, now in the other direction.
Yes, ma'am. We can say that to traverse from the start vertex S to Sn dash, we have to take one of these newly defined transitions from P to P dash, and it should be taken exactly once.
There exists exactly one new one transition. I'll call this M1 and M2. From M1 to M2 of the form delta P1 contained P dash is contained in delta P1, right?
Yes, ma'am. Ma'am, so we can break the path again into S to P, then P to P dash, and then P dash to Sn dash.
So consider, so the path will be of the form, path will be of form S to P, P to P dash to Sn dash. So I'll call this P1 and I'll call this P2, P2 dash. So now consider P1, P2, P1 concatenated with P2. This is a path labeled by xy in M1. So therefore, xy belongs to A. Okay, good. So any questions regarding the proof?
Ma'am, can you explain the reverse direction once again?
So this direction?
Yes, ma'am.
Yeah. So what is being discussed here is that you consider any string that is being accepted, any string that belongs to ln. So any string that is being accepted in n. Now it must be that it's starting at the start state and ending in some final state. And the final state was defined to be the final states of M2. M1 and M2 are copies of M. Now,
Yes, ma'am.
that means I am going, this Z, there exists a path labeled by Z such that you are going from S to some Sn dash belongs to F, final states of M2. So, the only way of doing it is, the way we have constructed it, the only way of doing it is, there is exactly one new one transition from M1 to M2. And the one transitions are of the form P going to P dash, P going to a copy of itself in M2. So therefore, this path must be of the form S to some P, and then from P to P dash, and then P dash to Sn. So some path from S to P, then P goes to a copy of itself, to the copy of itself in M2, and then there's a path from P dash to P dash to some final state in M2. So now let's call the path from S to P to be P1, and from P dash to the final state to be P2, P2 dash. Consider the equivalent, consider the corresponding path P2. So since there's a path from P dash to Sn dash, let's say, there will be a path from P to Sn because these are just copies. So I'm calling this P2. Then this will be an accepting path. But what is the label? If this was X, this is 1 and this is Y, which was defining Z, then this is also labeled Y because these are just copies of each other. So then that means XY is accepted by M1, means XY is in LM, means XY is in A. Fine?
Yes, ma'am. And you wrote that P dash belongs to delta P1. So should we
dash-
write equal to or belongs to?
Not equal to, right? Because this is an NFA now. So there can be more than one. There could have been a transition here as well. There will be a transition here with a 1 as a label.
Yes, ma'am.
Right?
It can be an FA, but if we define like this, will it be the correct one?
No, I don't know because I don't know exactly where. I mean, I'm not saying I don't know to your question. I'm saying I don't know where this 1 is going to appear. I don't know how this Z is going to be broken. So I cannot remove the transitions over here. But notice that this is a DFA. M1 is a DFA. So there will exist a 1 inside M1. There will exist a 1 transition out of P inside M1 itself, which I cannot get rid of. So there will
Yes,
be
ma'am.
at least 2 things like this.
Okay.
This is a proper NFA. I can't get rid of this one. Could I answer your question?
Yes, ma'am.
Okay, okay. Any other questions? Okay, so we'll go to the next question. So now you have a regular language L over sigma, some sigma. You have to prove that the following language is also regular. X in sigma star such that XX is in L. So this language is also regular. So this basically means that if I had a string something like ABAB in L, then AB would belong to this new language. Let me call this L dash. So how will you do it? So, firstly, I can assume that there exists a DFA for L. And suppose you have a string that is of the form X, X. So meaning that delta hat Sx is equal to P and delta hat Px is equal to Sn belonging to F. Let me write this as F. So basically in this path, just notice the structure. If the first transition here is, let's say, some symbol A1, the first transition from P will be A1. Second transition is A2, then the second transition will be A2, and so on. If the last transition is AN, then the last transition will be AN. So whatever you are doing in the path starting from Sn, you're doing the same thing in the path starting from P. And it's just that in the first path you're ending in P. In the second path you're ending in a final state.
Ma'am, can we build an NFA such that after we reach P, we make a epsilon transition to one of the final states?
But how will you know that? Because I don't know this P, right? I don't know which XX will be a good candidate. I don't know which will be a good candidate. I'll have to go through all strings in L to check whether it is of the form XX or not.
Okay.
And also one more thing, you have S2P, you have X. And now So suppose let's try and see what you're saying. So you consider S and you consider some path, some other state P. So that means you have a unique path going from S to P. Now you're saying consider the path from P labeled by X. Does it end up in S? Are you saying something like this?
If X, I mean, if there exists some path like this, then I make an epsilon transition
Okay.
from there.
You make an epsilon transition to this particular state.
Yes, ma'am. Like any one of the final states, like it is acceptable, right?
Okay, let me write
Del-
your procedure down. You're suggesting the following algorithm, right? So first step is consider a P, a state P. Like for each state P, let delta hat Sx equal to P. I know that this is a DFA, so there is exactly one path which is going to P. Okay, and now consider the state Q, which is equal to delta hat Px. So if Q belongs to F, then include epsilon transition
Such that
from,
delta,
let's say epsilon transition from P to Q. Okay, this is one step. Now notice that XX is still being accepted, right? Look at your procedure.
Then just change P to final state and make Q not a final state.
P to final state
And
and make,
Q not a final state.
but how can, I mean, Q can be a final state in its own right.
Yeah. Okay.
And
Yeah.
but if there are infinitely many such possible, uh, that means if L is infinite, then we cannot perform this algorithm exhaustively.
Why not this algorithm? Because you have for
Ma'am, there can be loops, right? And
right there can be loops also, right? Yeah, there is not, this is the shortest path that we can determine, not all x's. Right. Yeah, shortest path may not work. So let x is the shortest SP path. So the suggestion was this, but okay, now this may not be working. So anything else? Any other ideas? See, you don't know this particular P. You don't know where the middle point is for XX. So what can you do? So first, let me consider this particular language LP such that X in sigma star, XX in L, and delta hat Sx is equal to P. Okay, I'm being more specific. So notice that L dash is just going to be equal to union over all P and Q LP. Right?
Yes, ma'am.
Right. So now for LP, I'm just specifying this midpoint. I'm only considering those strings such that if you double that, the midpoint lies in P in M. Can you construct a DFA for this using M? Anything, not DFA, anything using M, you define a finite automata accepting LP. Because if I can construct for LP, this is a finite union. So I know that there exists a finite automata for L dash. So what if in my new, let's try to keep it a DFA. In my new DFA, I consider Q cross Q to be my set of states. Okay, sigma remains sigma. We'll come to delta dash, and the start state, we'll come to the start state also, and we'll have some f dash. So the start state I'm saying is S comma P. So I'm sort of putting down a finger at S and a finger at P, and now I'm trying to, I want my transitions in such a manner such that both the things can, I'm taking the same kind of transition from S as well as P. At every step, the path that I'm starting off from S and the path that I'm starting off from P, this Q cross Q is going to make sure that I take the same transition at every step. What will this delta dash be? What will f dash be? F dash also, let me specify. F dash is going to be P cross Q such that Q belongs to F. So meaning that I am trying to capture the fact that the first path will end at P and the second path will end at some Q in some Q such that Q belongs to F of Q is the final state of M. What can this delta dash be?
Like we can write
Delta dash.
delta.
Yeah, please continue.
Delta dash P comma Q comma X will just be,
Comma X,
let's
comma
say
A.
just anything. A will just be delta of P comma A comma delta of Q comma A.
Correct. Okay, so basically we are trying to capture the fact that whatever we are doing in the whatever sort of labeled transition we are taking in the first path, we want to do the same thing in the second path, but now in LP we have the added advantage that we know this particular midpoint. We are only considering those strings where they are of the form XX in L, but the midpoint of this XX, if you consider in the state, the state where we reach the midpoint is P itself. We are only considering those strings. If I do this, I know that since Q is a finite set, then I can just take the union over all such P's and I can show that L dash is regular. If I can show that LP is regular for any P, for any arbitrary P, I can show that L dash is also regular. So now my claim is that LP is regular because M dash accepts LP. Do I need to go further into the proof, or is it clear to everybody? Any questions? Okay, so I can move on, right? I'll go to the next question. So now I am considering similar problem, a little bit different. I am considering again L to be a language, has a regular language, so it has some DFA, and XY. So I'm going to consider in my new language L dash, I will include only those strings X such that XY is in L and there exists some Y in sigma star where length of X is equal to length of Y. Okay, so again delta hat Sx is equal to P and delta hat P, there exists Y such that delta hat Py is equal belongs to F and length of X is equal to length of Y. So now how will you do this? So again, if you look at the structure, there will exist a midpoint P where the first part is labeled by X, second part only has to take the same number of steps, could be labeled by anything else. It has to take there must be a path from P to a final state that has the same length as X. The labels don't have to be the same. So how will you design a finite automata?
Ma'am, we can again define LP such that it is all languages within it is the subset of L dash such that the midpoint is P. And then we can,
X belongs to L dash and midpoint is P. Okay. So
Yeah.
this is the claim. Claim is this is regular. Okay.
ma'am, then we can define a DFA on Q cross 2 to the power Q such that
You can define an NFA also. Why are you taking 2 to the Q? Try to define an NFA.
okay. Ma'am, so in the NFA, the transition from a vertex from a state P would be entire sigma if sorry union over all union over all transitions from Q to
So
to
union
B where
over
B belongs to
union over all transitions out of Q. Let me call this AI out of Q. Okay.
yes, ma'am. This would be delta of P comma A, comma, delta.
Okay, let me call this data. Yeah. Sorry.
Small delta,
Delta of P comma A,
comma, delta of Q comma AI.
what is S dash and F dash?
S dash is S comma P.
F dash?
F dash is P comma Q, where Q belongs to the final states of M.
So M I am just taking as Q sigma delta S F. Okay, so the idea is the following. I'm again taking Q cross Q and I'm designing an NFA, assuming that I'm designing an NFA for that language where the midpoint is going to be P. I'm accepting X such that X belongs to L dash, and the extra condition is that the midpoint of the string that certifies that X belongs to L dash of a string that certifies that X belongs to L dash is P. Okay. Now, what the NFA is doing is, if I consider, let's say X is some A1 to AN, then I just need to ensure that there exists a path of length X from P to some state. So I could take you consider any transition. P can have, P has a transition for each of the symbols in sigma. So consider all these transitions. You could potentially move to any of the states following any of these transitions. So that's why delta dash PQA is going to be take the union over all transitions AI that are going out of Q. Okay. Let me just write this as Q dash, because we don't want to confuse with P. So you take any transitions AI out of Q, you look at the state in the NFA that corresponds to delta Q dash A, comma, delta QAI. So that is this is the set of states I want to be at. This is the set of states that I can reach using when I'm reading A and I'm at state Q dash comma Q. Meaning that when I'm reading A, in the first state, I have a specific state. In the first coordinate, I have a specific state to go to. In the second coordinate, I have a choice of where I want to go to, because I just need to find some path that is of the same length as this path X. So every time I know I have to move one step forward, if I'm moving one step forward in the first half of the path, so let's call this P1 and P2. If I'm moving forward in P1, I know I have to move one step forward in P2, but I don't care what the label is. So that's why there are a set of states in which I can I can transition to when I read a particular label A, a particular symbol A. The start states now is just the singleton state S, comma P, because the first path, I want to capture these two parts, P1 and P2. The first part I know will start from S, and the second path I know will start from P, just from definition of L dash. For F dash, the final states, I know the first path ends in P. The second path should end in some final state of M. So that's why PQ such that Q belongs to F. Any questions? Any doubts regarding the construction?
So ma'am, P is given to us like S dash equal to S comma P.
I am specifying a certain P. Notice that for all P in Q, if I can show LP is regular, then the implication is L dash equal to union of LP, P in Q is regular, right? Because I'm just taking finite union over finite number of.
Yes, ma'am.
finite number of regular sets.
Yes, ma'am.
So this is the proof of the claim. Fine?
Yes, ma'am.
Okay, can I move forward? Okay, so now you get a variant of part A, but now I want that I want to accept X if X to the n belongs to L for some n greater than equal to 1. So earlier in part A, we saw that I want to consider X if X square belongs to L. Now I'm saying there exists some n such that X to the n belongs to L. Now how will you solve this? So, okay, so first answer this question. So if I had said, this is L dash, let me say L tilde, which is X sigma star such that X to the C belongs to L. So C is a constant. C is a specific constant. No. L to the C is X belongs to sigma star such that X to the C belongs to L. Suppose this was my language. Do you think this is regular?
Yes, ma'am.
Why?
Ma'am, we can just construct a C-fold Cartesian product.
Similar as part A, 6A. So you do a C-fold construction. Fine, right? If we were doing L2, we were taking Q cross Q and then doing the construction. Now we'll take Q cross Q to the C and then do the construction. We'll take C copies of Q. And remember which are the, so basically we are remembering what is the, I know that a path is of the form X, P1, X, P2, and so on. PC, no, PC minus 1, and then this final state, some final state. So I will basically specify this P1, P2 to PC minus 1, these points, these break points. If I specify L of P1, P2, PC minus 1, which means that this is a subset of L of C, and P1 to PC minus 1 are the breakpoints. Then similar to 6A, you will be able to make the construction and then you take union over all. So then LC will be equal to union over all P1 to PC minus 1 belonging to Q, L of P1 to PC minus 1, right? And this will also be regular because Q is a finite set, C is a constant, so this will also be a finite union. Finite, you're taking the union over finite number of regular sets, so this will also be regular. But the problem here is, so L to the C is regular, but the problem here is this is a variable, n need not be constant.
And can we take union of all?
Can you?
Like for each C belongs to N.
But will that be a finite number of unions anymore? So my question is, does this have to be a variable, or can you upper bound it by some constant, by some constant? Yeah. So notice that when I say, so this is related to L, right? L is equal to L of M, where M is this machine let's say it is formed by Q sigma SF. Suppose there are some K states in Q. So can you relate any of these constants related to M to show that this N will also be bounded? It will not be a variable. It cannot be infinite. Okay, so my claim is N will be, there exists an N if X belongs to L dash, there exists an N less than equal to K such that X to the K belongs to L. This is my claim.
And should it be x to the power n belongs to?
Oh, sorry. So if this is if this is possible, then you can do it, right?
Yes, ma'am.
If this is possible, then what somebody else was suggesting, you take you take the union over all LC, C going from 1 to K. Then I can show that L dash is regular. But how will you prove this claim?
Ma'am, we can assume that if x belongs to L dash, then there exists some t such that x to the power t belongs to L.
Okay, so if X belongs to L dash, then there exists T such that X to the T belongs to L, okay?
If t is less than equal to k, then we are done.
Yeah, so if T is less than equal to K, done.
Otherwise, is greater than or equal to k plus 1. And we see the final states of x, x to the power 2, x to the third,
Okay.
and so on.
Okay, so from S you're taking X first. Suppose it goes to P1. Then you take the second copy of X. Suppose it goes to P2, and so on. At every copy, so delta hat Sx is equal to P1, and similarly delta hat Sx to the I is equal to Pi. Okay. Sorry, it will be Pi. And now complete the argument.
Ma'am, I think we can define t to be the smallest natural number such that this happens. Then we can say that there must be a repetition of states in this in the set P1, P2, Pk.
There must be I comma j such that delta hat Sxi is equal to delta hat Sxj. Right?
Yes, ma'am. Ma'am,
And then?
So we try to see delta hat of.
So I'll just say I is strictly less than j. Now.
We try to see delta hat of s comma x to the power t minus j plus I.
T minus j plus I. And this will also be equal to delta hat of s of x to the t.
Yes, ma'am. So t minus j plus I is strictly less than t, which contradicts the minimality of t.
Contradicting? This is minimum. Minimum such t. Okay, good. So basically what he's saying is you consider all the copies of x in x to the t. Look at the end states of each of these copies. So I'm going to go from pi to pi plus 1, let's say, for the ith copy. But since I have only k states in my finite automata, and there are k plus 1 such appearances of x, there must be at least one I and j, I strictly less than j, such that the end state of, okay, sorry. Yeah, this is fine. Such that if you look at the end states, then they will be the same. If they are the same, you take out, so suppose suppose x to the I ended in P2 and then x to the j ended back in P2. Then his claim is you leave this part out. You follow x to the I and then you follow the rest of the copies of x to whatever final state there is. This is a shorter string. This will be x to the t minus j plus 1 plus I. And then t minus j plus I is strictly less than t, which contradicts the which contradicts the fact that t is the smallest number for which x to the t is a certificate that x belongs to L dash. And therefore we are done. So if we can prove this claim, we know that if we can prove this particular claim, then using the fact that finite union of regular sets is regular, we can show that L dash is regular. Any questions? Okay, so quickly we'll go through two more. What is the time? Yeah, quickly we'll go through, in 5 minutes we'll go through two more problems. So 0 plus 1 star is equivalent to 0 star plus 1 star. Is this true or false?
Ma'am, false.
Why?
Ma'am, the string 0, 1, 0 would belong to the left hand side, but not the right hand side.
Okay. So in fact, any string of the form 0 star 1 star 0 is in LHS but not RHS. You can find other such sets like infinitely many strings. Okay. Part B is 0 star 1 whole star is equivalent to 0 star 1 star star. True or false?
True.
True. Why? Prove it. Consider this particular string.
Ma'am, false.
So
0, 1, 1 belongs to 0, 1, 1, 0, 1, 1. Let us say we take this. It belongs to RHS but does not belong to LHS.
Why does it not belong to LHS?
It will be like some
Right.
zeros followed by single one and again 0 followed by 1.
I mean,
There
there can be
cannot be
zero
consecutive
zeros, right?
ones.
There can be zero zeros
Yes.
between
There
two
can be
ones.
consecutive ones because
Yeah, there
zeros
can be
are
zero
not-
zeros.
This will not work.
This will, but you're close. So why don't you try this one? This 0, 1, 0.
Okay, ma'am, it will not be a part of RHS.
0, 1, 0 will not be a part of LHS.
This will not be
Yes,
part.
yes, LHS.
Not be an LHS. So this particular subset of infinitely many strings will also not be part of LHS, but it will be part of RHS. Okay, good. So last question. So I'm giving you a regular expression alpha, which is a plus b star, ab, a plus b star. Now you have to give me a regular expression for not of alpha if first sigma is AB and second sigma is ABC. So let's consider sigma is AB. What are the strings that are contained in not of alpha? By definition, L of not of alpha is not of L alpha. Okay, what are the strings that are contained in this?
And B star, A star.
Okay, good. So basically, the strings that do not belong to the language L of alpha are those strings where all B's appear before all A's. If there is a B that appears after an A, then notice that it's going to be okay. First thing is it is possible that there are only B's. If there is an A, there are only B's and there are only A's. If there is an A and a B, it must be true that all B's appear before A's. So L of alpha is equal to A star plus B star plus the language, or let me say L of A star, L of B star, plus the language X in AB star such that all B's appear before A's. So this in particular is B star A star. So, and now I think it will be easy for you to prove that A star plus B star plus A star plus B star A star is equivalent to B star A star. Please try to show this. Okay, so this is part A. What about part B? Let sigma be ABC. Then what are the languages that are not in L of alpha? Notice that there is no C in alpha. So there's no C in this regular expression. Now what are the strings in the complement language?
Anything containing C.
Anything
And-
containing C?
And
And
then
B star, A
B
star.
star.
Plus B
Okay.
star, A
How
star.
can you write anything containing C?
C star.
Uh,
At least
C
one.
star.
No. At the rate C at the rate. That should work.
Once more. At
At
the
C.
rate, C at the
C.
rate. Okay. This is not a regular expression, right? Because at the rate cannot be
Yeah, I
part
mean,
of.
then we just do A plus B plus C whole star for at the.
Correct. Okay. So then basically L of alpha, not of alpha is equivalent to A plus B plus C star C, A plus B plus C star plus B star A star.
Ma'am, can we do
Yes.
something like B plus C star, A plus C star?
B plus C star, A plus C star,
Yes, ma'am.
whole star. And then
A plus C whole star.
A plus C whole star and then C.
No, ma'am, that's it.
This may contain this will contain this will not contain something like ACB, right?
Oh, okay, ma'am. Okay, ma'am. Yes.
Yeah. Okay, so any questions? We are done. So if you have any questions, let me know. We are also a little bit over time. So any questions?
Now, the previous example which Anubhav gave, that was, I think, right. Can you please explain it once more?
Which one? For
The same
question
question,
8?
that B plus C star into A plus C star.
B plus C star into A plus C star. So ACB belongs to not of alpha. It belongs to the language not of alpha. How will you match this?
Oh, okay, got it.
Yeah. Okay, anything else? Any other questions? Any questions from before? Okay, so I will upload the new version on Teams, and it will also be uploaded on the website. If you have any questions, leave it in the post section or ask in the next class. Okay, thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.